Hey guys, welcome to Safi Next, and let me start from a statement: quantum inductors, a new discovery which is hoped to bring another twist and shape of devices working on the basis of modern technology. In this video, I present a very quick review about a research paper very recently published in the October 2020 issue of Nature. The researcher of the paper belongs to Japan, and the corresponding author of the paper is Tomoyaki Yakochi. The authors of the paper reports an amazing discovery of inductor working on the principle of quantum mechanics and is named as Emergent inductance. What would be the fascinating effects of quantum inductors in boosting up the coming days technology? I would like to come to this point later and would like to first answer very briefly the question of what a conventional inductor is. An inductor is one of the most important ingredients of electric and electronic circuits, which works on the basis of Faraday's law of electromagnetic induction and store magnetic energy given by Li squared divided by 2, where L is called inductance and I stands for the input current. The voltage across an inductor is directly proportional to the rate of change of current flowing through it. It consists of a coil made from a good conducting wire and a core. An unfortunate reality related with the conventional structure of inductor working on the basis of classical electromagnetism is that the inductance L is directly proportional to the area of cross section and to the number N of turns in the coil. Generally speaking, the inductance in a conventional inductor is directly proportional to its volume. That is, L is directly proportional to N times area of cross section, which can approximately be set equal to volume. Due to this reason, large inductance cannot be obtained from an inductor of small volume. This is a drawback of conventional inductor in using them in small sized electronic devices. To overcome this difficulty, the idea of kinetic inductance, a mechanism for generating inductance from superconductor, was introduced. In this mechanism, the inductance is inversely related to the cross section, a desired characteristic. However, the use of superconductor in traditional devices have their own technical limitations and is of no benefit presently due to its non-availability at room temperature. This new mechanism for the discovery of emergent inductance reported in the paper under present discussion works on the principle of quantum mechanics. Most importantly, this device does not require a coil or a core. It is expected that this will help in optimally resolving the issue of producing large inductance with a very small size inductor. Now let us understand the emergent inductance by linking it with emergent electromagnetism or emergent fields. Emergent electromagnetism refers to electromagnetism in which the generated electric and magnetic fluxes are described by a concept in quantum mechanics called a Berry phase. Emergent electromagnetism can be realized in magnetic system characterized by non-collinear spin structures. A non-collinear spin structure refers to the structure of material in which the orientation of spins is a function of the position of the spins in a lattice. Such structure could be, for example, in the shape of a helix as shown in the figure. When electrons constituting electric current move through such structure, they get strongly correlated with the local spins of the lattice and picks Berry phase. This phase works as an effective electromagnetic field and is called emergent field. Yamauchi and his colleagues used this idea on a magnetic material with chemical formula GD sub 3 RU sub 4 AL sub 12, where GD, RU and AL respectively stand for gadolinium, ruthenium and aluminium. This material preferably contains a helical non-covalent spin structure. The author investigated the inductance on micrometer scale of a magnet and found that the emergent inductance is inversely proportional to the cross-sectional area of the structure. In the abstract of the paper, Yamauchi and his colleagues writes, in a microscale rectangular magnetic devices with nanoscale spin helixes, we observe a typical inductance as large as 400 nanohenry, comparable in magnitude to that of a commercial inductor, but in a volume about a million times smaller. The observed inductance is enhanced by nonlinearity in current and shows non-monotonous frequency dependence, both of which results from the current-driven dynamics of the spin helix structure. The magnitude of the inductance rapidly increases with increasing device cross-section, in contrast to conventional inductors. Right after 2 weeks of the publication, another report on the paper published in the same journal, which you see on the screen. The author writes, Yamauchi and colleagues' work is important for several reasons. First, it offers a scalable approach for developing miniaturized high inductance inductors which could be used in many micro or nanoscale electronic devices and integrated circuits. Such inductors would also be much simpler in design than our conventional inductors because a coil and a core would not be needed. Secondly, the work opens up exciting opportunity for constructing highly efficient hybrid spin electronic circuits and systems. And third, it serves as a proof that a fundamental concept in quantum mechanics, that is the Berry phase, can lead to real-world applications.